Now that is the fourth video of our MLE sequence for the linear Gaussian regression model. And in that video, I'm showing you step by step how to determine the standard errors of the maximum likelihood estimates for that linear Gaussian regression model. Now, as that is already the fourth video of the sequence, I will assume that you have seen at least the video on finding the ML estimates of the linear regression model. That's mainly to ensure that you have seen the notation that I used before. So let's start. The variance covariance matrix of the parameter vector theta, which I denote here as hat variance of theta, coincides with the inverse of the information matrix. I denote the information matrix as capital I. Now I itself is the negative inverse of the expected Hessian matrix. So let's write that down with math notation. Now looking at the equation, you see that we have to do three things. First, we need to determine the Hessian matrix h of theta. Well, that is nothing else than determining the matrix of second derivatives of the log likelihood function. Second, we take the expectation of that Hessian matrix. And third, we invert the last expression and multiply it with -1. Now in that video here, we will do all of that on a step-by-step basis. So let's do step number 1. The Hessian matrix is the second derivative of the log likelihood function. That is the same than the first derivative of the respective Jacobian. We therefore start off with writing down the Jacobian of the log likelihood function. Mathematically, that reads as follows. Now notice that each element of that Jacobian vector was derived in the previous video, so I now take that as given. But to give some background information, the first entry gives you the gradient when you look for the partial derivative of the log likelihood function with regard to beta, and the second element gives you the partial derivative of the log likelihood function with regard to the sigma square. Okay, now what we now have to do is to take the derivative of each of these elements of the gradient vector with regard to beta and with regard to sigma square. That's a bit painful right now, but as I've said, the video is step by step, so let's just do everything step by step. So we want to determine the second derivative of the log likelihood function with regard to beta square. Therefore, we have to get the partial derivative of the first element of the Jacobian with regard to beta. And that means we need to find the partial derivative of x prime y minus x prime x beta over sigma square with regard to beta. The first term doesn't depend on beta, so what we end up with is minus x prime x divided by sigma square. So that's the first out of 4 elements. Let's go for the second. Now we want to determine the second derivative of the log likelihood function with regard to beta and with regard to sigma square. Yeah. So here mathematically is what we want to do. Partial derivative of x prime y minus x beta over sigma square. With regard to sigma square, we see sigma square is in the denominator. It appears once, and therefore the respective partial derivative will be minus x prime times y minus x beta divided by sigma to the power of 4. Now note that y minus x beta is simply epsilon, so we can rewrite that entire expression here as minus x prime epsilon divided by sigma to the power of 4. Okay, let's continue to the third element. We now want to get the second derivative of the log likelihood with regard to sigma square and with regard to beta. So therefore we take the respective Jacobian term for sigma square and now build the derivative with regard to beta. Now looking at the term, you already see that the first term minus t over 2 sigma square doesn't depend on beta. y prime over y doesn't depend on beta. So it's just these two last terms which depend on beta. So the respective partial derivative will be minus 2y prime x plus 2 beta prime x, everything divided by 2 sigma 4. Now we cancel out the 2. We end up with minus y prime x plus beta prime x over sigma 4. And now we just regroup terms and rewrite that as minus 1 over sigma to the power of 4 times y prime minus beta prime x times x. And since epsilon is just y minus x beta and epsilon prime is y prime minus beta prime x prime, we rewrite the last term as minus epsilon prime x divided by sigma to the power of 4. Alright, we are done very soon. We need the last element of the Hessian, which is the second derivative of the log likelihood with regard to sigma square and sigma square. So again, we write down the respective Jacobian term for sigma square, and now take the first derivative of that term with regard to sigma square. Now sigma square shows up in the first and in the second term, so not surprisingly, the derivative will be capital T divided by 2 times sigma to the power of 4 minus y minus x beta prime times y minus x beta prime divided by sigma to the power of 6. Now rearranging terms a little bit, basically just recognizing that y minus x beta is just the epsilon, gives us the solution t divided by 2 times sigma to the power of 4 minus epsilon prime epsilon over sigma to the power of 6. Okay, thus we now determine the Hessian matrix of the Gaussian linear regression model. And I'm just showing here once again, in summary, what that looks like. Okay, so now we continue with step number 2. We need to take the expectation of the Hessian matrix. So in the equation here, you see explicitly what we have to do. Now, interestingly and very nicely, since one of the assumptions of the linear regression model is that the expectation of x prime epsilon is 0, meaning that the white noise shocks are not correlated with the explanatory variables in X, the off-diagonal elements of the expected Hessian need to be 0. And thus, the expectation of that Hessian simplifies to this matrix here, where on the main diagonal we have the entries, while on the off-diagonal elements everything is 0. Okay. Now notice for the last element, the minus 2 over minus t divided by 2 sigma 4, we've exploited the fact that minus the expectation of epsilon prime epsilon is simply minus sigma square times t. So there was some cancelling going on. Okay. But the good news is we've found the expectation of the Hessian, and therefore we can move on to the last step. So the final step requires us to compute the inverse of the information matrix. The information matrix coincides with the negative of the expectation of the Hessian. Therefore, we can just write it down like the information matrix of theta is minus the expectation of the Hessian. Now, we just determine the expectation of the Hessian, multiply in the minus 1, and what we end up with is the diagonal matrix with x prime x divided by sigma square as the first element and t divided by 2 sigma 4 as the second element on the main diagonal. Now finally, the inverse of the information matrix, since all off-diagonal elements are 0, the inverse is really easy. Just take the inverse of each diagonal element itself, and you therefore see that the inverse of the information matrix takes this nice, simple-looking shape. Now, if you look at that, you basically see that we've determined the variance matrix of our maximum likelihood estimates. Since that was so much work, let's just be proud and write it down once again and celebrate, yeah, that the variance for the ML estimate is simply the diagonal matrix with sigma square x prime x to the minus 1 as the first element and 2 times sigma to the power of 4 over t as the second element. Okay. Now, if you look carefully at that last matrix, you notice that sigma square x prime x to the minus 1, which stands for the variance covariance matrix of the maximum likelihood estimate beta hat. Now that in fact coincides with the variance covariance matrix of the respective OLS estimate for beta. Now that says that not only are you getting the same maximum likelihood estimate for beta compared to the OLS solution, but you also get these estimates with the same precision. Hence, there's no advantage of using maximum likelihood over OLS if your problem is a linear Gaussian regression model. On the other hand, the method of OLS left the variance covariance matrix of the white noise variance term unspecified. We had that in a previous video. But if you use maximum likelihood, you get an estimate for the variance of the estimate for sigma square. Yeah, so you see that maximum likelihood provides you with more information than the OLS counterpart.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.